which is not important. So you're comparing how much work does the active force compared to how much can do the thermal activation from the normal environment with which the particle is in contact. Okay, so this is a summary of the motion of a single particle, but now another special feature about active particles, and Fred also mentioned it, but I remind it here, is that they behave very weirdly with respect to what happens when they get close to a wall. So when they get close to a wall, they tend to remain close to the wall for longer than what would do a normal Brownian particle. So for example, this is from experiments, the Leonardo and company are summarizing what's going on, and what you see is that the particles will spend a lot of time, close to the boundaries, because it's sort of they attach to the boundary because they start, pushing towards the boundary, and until they turn, they stay there. Okay, this is another feature. They tend to aggregate close to walls, the active particles. Okay, so now let me tell you about the models that we propose to make this quantum. So we have 3 models, and they are different realizations that, they have their own good properties and bad properties, each of them. So the first one is kind of similar to what Fred was discussing in the first lecture, where he had particles moving on a lattice with some rule. So here we will have a quantum particle jumping from side to side on a 1D lattice. It will be in contact with some environment that it will give it, sort of transition probabilities to go right and left, but at the quantum level, which will be different. And then there will be another element in the Hamiltonian that will be the normal one that would correspond to the model, if we wish, of an electron moving just on a single line. But the special feature of the activity will be given by these other, you will see, elements in the Lindblad equation that will make its motion a little bit bizarre. Another purely quantum problem that we proposed is one in which we have a particle moving on a continuous line on one axis, normal particle, just kinetic energy it has. And then we are considering that it also has an internal degree of freedom, which is like a spin, a vector, up and down, just a quantum spin. And that this quantum spin is coupled to an environment that is making flip in some way. And the spin is coupled to the motion of the particle itself. So you will see the Hamiltonian. So there will be a coupling between the spin and the momentum of the particle. Both the spin and the momentum of the particle feel the environment in some weird way. And this will make this particle move in a similar way to the one that I have discussed before. And then the third one in the middle is more similar to the Ornstein-Uhlenbeck model, in the sense that we have a particle coupled to a quantum bath. It's a quantum particle coupled to a quantum bath, and on top of that, there is a classical noise that also acts on the motion of the particle. And this classical noise, we make it have a time delay tuned in some way that will also make the motion of this particle a little bit bizarre. So the middle model is the mix of classical and quantum, while these 2 other ones are purely quantum. And the way we model this is through the Lindblad equation that I introduced yesterday a little bit fast, but okay. So when you have to describe, the time evolution of a quantum problem in a state that you don't know very well, you use this density operator, which is, this superposition of operators that correspond to elements of the basis of the Hilbert space with probabilities. Anyway, so you have a Lindblad equation that tells you how this operator evolves in time. This is the normal way in which we would do it if it were completely isolated from the environment. But then we have the Lindblad operators that tell you how the bath acts on the system. And from this rho hat, which depends on time, one can measure observables, and in particular, one can measure mean square displacements, variances of the position, and different kind of quantities. So, okay, the comments which you cannot read are the ones which I said yesterday in the talk. So if you know the time dependence of the rho hat, you can compute quantities like this one, for example, the variance of the position of the particle, which is similar to what I was telling you about the mean square displacement. You can also calculate the mean square displacement if you wish. So what it is just, okay, the expectation values here are not averages over noise. They are, how do you compute them? You compute them as traces of the operator that you want to evaluate times the density operator at the time that you evaluate. So in this case, for example, it's a local measurement in time that we are doing. And then we just need the rho hat of t to use it in this way to calculate everything which is here. And from the time dependence of this, you will see that there are interesting features arise. So let me give you the results, more details on the models and the results. So the Hamiltonian of the model alone is just a problem of hopping of particles on the lattice, just like what Fred was saying. So this is my particle. You can go right or left with controlled by, these jumps being controlled by parameter j. And then I labels the site on the lattice, and like this you can see that, okay, one of the terms is moving to the right and the other one is moving to the left. And what we do is that we have a dissipative hopping with these Lindblad operators that we choose to be that kind. And we plug this into the Lindblad equation. We solve the Lindblad equation with different kinds of tricks that my collaborators know very well because they have been working on these problems for long. And basically what you do is you compute this variance of the position that I told you before. And what you find is that indeed, as a function of time, if you choose the parameters in an intelligent way, so if you choose this j and this gamma and this other gamma in an intelligent way, what you will see is that there are three regimes that appear. There is diffusive regime, a ballistic regime, and another diffusive regime that appear in the behavior of this quantity. And you can analyze how this depends on the different parameters. Okay, so it's basically J over a combination of this gamma L and gamma R, which controls how much you separate these regimes. Fred?
Can I interrupt you?
Sure, of course.
Yeah, so you're dealing with fermions here. So
if you wish,
and
yeah.
you could have dealt with
bosons.
Yeah,
bosons.
Yeah. But of course you know the quantum nature of the particles only if you have many of them. So the density should appear and should affect your results here, shouldn't it?
The density?
If you
I have a single particle, huh?
You have only one.
Yeah.
Only one.
I have only one. I didn't say it, but I mean the I mean the sector of just one particle. Everything I will say is for just one particle. Yeah. Okay, so I realize I don't have the first ballistic regime, but okay, I don't really care about that one because it was a little bit negligible even in the classical case. So I have a normal diffusion ballistic, and this is the interesting active one if you wish, and then another diffusive over there. I can tune, as I say, how I separate these regimes with tuning the parameters. But then another nice thing about this problem is that I can put walls. I can consider the case, this had been done for periodic boundary conditions, so there were no walls. But then I can also consider an open chain where what happens at the border is different. So I have a wall. And if I go to the border, I have to come back. I can only come back. And then what I see is that, again, depending on the parameters, I see a concentration of particles close to the walls. So this is the density, what is plotted here. And depending on the parameters, you see the particle is only one particle, I insist. So the particle will go to the wall and it will remain close to the wall in this steady state. So I have these special effects of the walls with this model. Now, let me tell you about the third model, the other one which was completely quantum. So here, the model that we choose, the Hamiltonian, is like this. It just has the kinetic energy term, and it has a kind of weird coupling, if you wish, but okay, it's a coupling between momentum and the spin of the internal degree of freedom. And then I choose the Lindblad operators in some way that act on the spin, but also act on T. And again, if I compute this variance of the position, what I see is that I have diffusive, ballistic, diffusive, and there is still, for this problem, in the very end, the key, this part is dominating and it goes to ballistic again. But still, I can cook up the parameters in such a way that I don't see that one, and that I only can focus on this, and then I have these three regimes as in the classical problem. And both in the previous case and in this one, I can compute the diffusion coefficient in the last diffusive interesting regime, which would be, the equivalent of the dA that I had previously. And for example, for this problem, I can see how it depends on the parameter lambda, which is the strength of the coupling between spin and momentum, and the Lindblad coefficients of the coupling to the bath that I have over there. Okay. And then the other one, which is probably the easiest to grasp, to understand, is just the problem of a quantum particle moving on a line, just a normal one, again, only kinetic energy. But then I consider two baths. I consider a quantum bath of oscillators, like the ones I was discussing in the lectures, with a linear coupling between the position of my particle and the oscillators. I can choose the spectrum of frequencies of this bath, putting the spectrum, choosing it in a convenient way. And then I can also choose what is the classical noise that I also couple to my particle. I choose it to have zero mean and exponential correlations in time with a characteristic time, which is another parameter in my problem. So this problem can be solved not with the Lindblad equation, but more with the generating functional method that I very briefly sketched yesterday by the end of the talk. So it can be solved completely like that. And here we computed directly the mean square displacement. And the mean square displacement, again, has these three regimes. And for this problem, in the absence of the coupling to the classical bath, that is the new aspect here, in 1D, for these quantum particles, quantum Brownian motion is logarithmic in time. This is known since, I don't know, 40 years ago. So this is the dashed line which is there. It's a logarithmic function of time. But then you see that from the logarithmic function of time, there is the ballistic part that induces the new path, and then there is eventually another, a final diffusive regime. And here one can also compute what is the diffusion coefficient in this last diffusive regime. So instead of writing diffusive, actually for the first one, I should have written subdiffusive, because it's not diffusive. The first one is logarithmic. Okay, so I gave you, these analytical models with which one can do a lot of calculations, and they are very simple to work with. Now, realizations, well, I've been told by people who know more than me that these things can be made in the lab. So model A, this hopping, that is induced by the coupling to the bath can be induced by acting with a laser on the particle. So this is what is called in the literature laser-assisted hopping. For model B, for the last one, this is more traditional. So, you can model these ohmic baths in different ways. And there are different ways to model the particle as well. So impurities in cold atoms, for example, this is like one, even I worked on this in the past. So it's one atom in contact with many other atoms of a different species, for example. And people doing atomic physics can confine these with lasers and things like this. So this would be just the particle in contact with the quantum path. But then you can add a classical noise of a different kind, non-Markovian classical noise. This is also easy to implement in this context. So the model B, the active Ornstein-Uhlenbeck particles, could also be realized in the lab. And the last one, spin to momentum coupling, is also can be engineered in atomic physics. So in principle, these things can be done. So now perspectives, of course, I only work with a single particle, so it's a little bit boring. So what I told you at the beginning, which is what we like to do, statistical physicists, which is to look at collective phenomena. Of course, I'm not looking at collective phenomena here until now. Now, what one would like to do, here it is. So what we'd like to do is to eventually put many of these particles together, make them interact, and try to see, how do they behave. Of course, this is very difficult, but just let me tell you something about what happens with classical active particles on 2D. So they can have very complicated phase diagrams. They can have very complicated many phases of different kinds. So they can have solid phases, what is called exotic phases. They can undergo MIPS, motility-induced phase separation, that Fred also explained in his lectures, depending on density and the amount of activity that you include in your problem. So the challenge would be to try to understand something like this, working with one of these problems that I told you about. So of course, these kind of phase diagrams, I got them in collaboration with my friends in Barcelona and Bari. But of course, you cannot do quantum simulations with many particles like we did here. There were millions of particles, right? So we have to do something else. What can one do? Well, one can try to adapt field theoretical methods that people have also used in the context of classical active models, like also models that Fred mentioned, this active model B, B+. All these things can be made quantum and can be considered to be coupled to quantum and classical baths, and eventually perhaps can be studied. And things about quantum MIPS perhaps can be also accessed. I don't know. I mean, this is a part of the project, the thesis project of Jean. So we'll see. Anyway, so this is the perspectives, and it's still not done. So I finish here.
I will have time for 2 questions.
So, from this perspective, would the quantum task set be considered active, or is there some kind of...
A little bit like the TASEP. Yeah, the first one is like the TASEP. I fully agree with that. Yes. Yeah.
So intermediate between interactions and the ideal gas, there is many body, but without interactions, and quantum statistics will play a role.
Yes.
And you have any clue what's gonna happen?
No, good question. Yes.
And
Yeah.
I have another question. So when we describe quantum Langevin equations,
Yes.
We can also take the limit of the bath, of the temperature of the bath going to 0, and then there remains a diffusion that's quantum driven, which is logarithmic.
Yeah.
What's going to happen if you keep your active part and go to 0 temperature?
Well, this is in this case that we have this logarithmic diffusion there is that one. Yeah, is that one.
Okay.
Yeah. So this bath we took it to be at 0 temperature.
Okay.
Yeah. Yes.
The last example, I mean, the example C.
Yes.
Because it looks to me that it can also be modeled. I mean, the last term, I don't know, but pretty much the system looks like a quantum walker in which you can take the coin as the spin.
You can take the, sorry?
I mean, when you have this quantum walker,
Yes.
then you have the coin, so to say, which is an extra degree of freedom that is
The coin. Yes. Sure. Yeah.
So have you looked into the simulator? But this looks pretty much like something you can do with that, with a quantum walker.
But this it is well, a quantum walker. What do you mean by a quantum walker? This is a quantum walker, no?
Yeah, but really a quantum walker. So just in one dimension, you could put some sides and do.
Yes, to do it in the discrete on the discrete.
With the coin being the extra.
Okay.
Which is the spin.
Yes, maybe. Okay, we didn't do it. Yes. No, we haven't thought about that one. Yeah.
You also go and look at this kind of behavior.
I understand. Yes. Yeah.
Thank you.
You're welcome.
Yo me desconecté porque nadie me daba bla.
No, sí había.
Sí, nada. ¿Está el micrófono y cámara o no? ¿Quieres acá? Ah, desde. Desde no.
Yeah. No, in Italy they are like this. No, in France, no. In Italy, we do very, and they try to-
Ayúdame porque aquí. Ah, no, ya, ahora sí. Listo, y entonces, ¿dónde comparto? ¿Me está grabando?
They try to- no, here it's 15 minutes late, so-
Listo. Entonces, español, ya decido.
Como quieran.
Español o en inglés.
Como quieran. English, okay. That give me more time.
Yeah.
Okay, and our next speaker is Rafael Hurtado.
Okay. Okay, good afternoon. So we are going to talk about chess. This work is with Gustavo Muñoz. He's a student there at the Department of Physics at Universidad Nacional de Colombia. So we are going to talk about the game itself, the representation. We are going to use graphs, entropies, and at the end, very short about the complexity indices. So how is the game? I guess that most of you play chess. So it is just, for myself, it is important to say that it requires a massive amount of accumulated knowledge, which is part academic, related with the openings, and part is related with the rival. So, okay, we have like a difference in time. So we have the board, the pieces, rocks, knights, bishop, queens, kings. And what is important for myself is to tell you that we are going to work in the descriptive notation. It is different here than here, but anyway. So we have the pieces, we have the columns, which are indicated by the queen or the king, and afterwards because with the adjacent pieces and the row. So if you, it is different just what I see here than what I see here. Okay, so this is, for example, pawn, queen's rock 4. It means that it is the pawn, queen's rock, it is the column, 4, it is just a row. So it is the notation that we are going to use. And now we are going to count the first move. It is just, we are going to work just with the first move. We have 8 for the pawns, moving just 1 square, another 8, moving 2 squares, and 4 for the knights. So we have 20 possible moves. For the whites, we have exactly the same thing for the black. And so as they are independent, we have 400 possibilities when we put all together. If you want to see a bit more, when you get to the third move by the black, you have more than 9 million of positions and 120 million ways of getting into those positions. But not all of them are useful. You have just this number of named openings. It is relevant openings in chess. So the representation, we use graphs. It is just like, for example, this move, pawn king 4, pawn king 4. So it is going to be a buckle or a loop into the same node. Then for this one, we are going to have these 2 nodes with the arc. And if we put together many matches, then we can construct a graph or a network, which would have 20 nodes, and we can associate it to a matrix. This matrix would have weights related with the number of times that each combination has been played, for example, for a player. Let's see what happened with Karpov. Sorry, it is not going at the same velocity. So this is the matrix. When Karpov plays white, you would see that it has 1, 2, 3, 4 different moves of the first one, and he has like I remember maybe 8 when he is playing with the black. Let's see another player, which is Magnus Carlsen. Sorry, there is a problem with the computer. We are not going at the same. Okay, so how does he play? He plays in a very different way. He has like 12 alternatives for the first move when he plays white, and about 11 when he plays black. These are, sorry, this is, for example, this is the adjacent matrix. It means did it play it or not, and you can weight it. So it would be, this would be like the weighted matrix. So when you have the network, sorry, okay, no. Okay, so when you have your network, you can define the degree, the out degree for any one of these nodes, which is going to tell you how white moves, how blacks replace when whites move, and the in degree, which is going to tell you the opposite information. Very important, when you see out, you are talking the black pieces. When you see in, you are talking about the game of the white pieces. Then we define also and the strength of each node, which is just adding the weight of the arcs adjacent to each one of these nodes. So let's go to make the game of entropies. So this is a very ordered system, at least from my mother's point of view and my wife. When I just use my phone, my cell phone in the bathroom, it is clear that it has to be there. But if I use my cell phone everywhere in my house, I would say that it is quite disordered in some way, or I would be quite disordered, and there are many more alternatives for finding the cell phone, and I would say that it is related with diversity. Then we will make the same. Okay, no, then we will talk, we are talking about diversity. We will construct an entropy quantity, which is similar to the Boltzmann entropy, just like the log of the degree, both for the out degree and the in degree. And then we are going to add for all of the nodes, the 20 nodes of the network. When we talk about the weighted network, we talk about preferences. It means that it is much more probable to find my cell phone in the bedroom than in the bathroom. Then I can make also the game of defining an entropy. In this case, would be similar to the Gibbs-Boltzmann entropy. And there is one thing which is important. The entropy, which is related to the degree, will be the upper limit to the entropy, which is related to the strength of each node. So having this, let's go to the system. It is the Olympiad from the beginning, 1924 to 2020. And the Olympiads are these ones. Then let's take 1 minute in this one. So I said in, so we're talking here about white. Out, I'm talking here about what is doing, what black is doing. So let's see first this part. The upper entropies are related, are certainly those that I call the Boltzmann entropies, which are the limit for the upper limit for the other ones, which I call the Gibbs entropies. And what it means here is that there is a quite strong system of preferences for the white pieces. Instead, when you look at the black pieces, black pieces would have to get along with diversity. So white ones, preference, black ones, diversity. This is just like, what is going on with this again? Okay. So when you look at how the entropy would change with time, with each year, you can recognize, maybe I would go back, sorry, just one time. Look, it is going further back. Look at these times. This is the first era. It would be like the beginning of the game. This part would be the Botevnik era, which is the Russian schools or the Soviet schools of chess. This is Kasparov and Karpov time. And it is like the new time. So you can see that you can, in some way, divide make sections in the time related with the different tables of the game as a whole in these times. I was saying here, early, Podvilnik, Karpov, Carlsen are the main representatives in this time. So there is a question, and here I would have the entropy for the network for all moves. And each one of these three would be one for the matches when whites win, the other one when black wins, and the other one when there is a draw. So the question is, can I add up these entropies to find the one of the total, let's say, set of matches? And you can see that it is not so. So then what you have to say is, okay, we want to explore additivity, and then if it is not true that this part is equal to this part, it is for the whole network and it is for each one of the subsystems. So what should be around here so that we can make it to add? And then we go to Thales entropy. In the case of two subsystems, it is written in this way with a factor, with an index, which is the Thales or the additivity index, which is called Q. So this is like what should function in the case where you have, depends on the Q, strong correlations or in some way certain constraints. In the case of three subsystems, which is ours, whites, black, and raw, then we have to write it in this way. We are going to be worried about the ratio between this quantity and this quantity. If it is 1, it means that Thales pseudotivity holds. If not, let's see what happens if it doesn't hold. Thales entropy, in this case, it is for the degree, and this one out, in. And the other one, it is for the strength, just in a similar way as we defined it for the previous case. So let's explore a bit. If we make Q equal 0.5, maybe I will make you clear one thing. Notice that we have 1 minus Q. When Q is 1, we can recover the Gibbs-Boltzmann entropy. You just have to make an expansion. And so we are going to explore when Q is smaller than 1. And it resembles a bit what we saw before. When Q it is equal to 1.1, it is very close to the situation in which we would have like the Gibbs-Boltzmann entropy. Okay, it will resemble very much to our original graph. And now we go farther to when Q is equal to 2. What does it mean Q to be larger than 1? Q to be larger than 1 means that there are correlations inside the system. So we are going to see a bit about that. So these graphs, what they are doing here is the Q, the Salis index. These are the years. Sorry that they are not very clear. And we are going to have this ratio that we defined before. And this is the surface. It is not exactly surface because it is discrete, but for each year you will have the curve related to the value of the entropy for the different values of Q. There are two planes. The first plane, which is this one, tells you that Q is equals to 1, and the other plane tells you that the ratio is equal to 1. So we're going to explore what happens. This is for the other entropy, and then we are going to explore, we're going to see which is the value of Q in each case. So first, we're going to see which would be the value of Q when you have the maximum of this ratio. And this is what you see. And you can recognize some of the motives, I don't know, the behavior that we saw before. And for example, I can say that this is the time of Vodviznik, of the Soviet era. This is the time of Karpov. This is the time of Carlsen. In this case, we're talking about black and white as before. Please notice that this is decreasing with time. What it means is that we started with very strong correlations, and these correlations are diminishing with time. Let's explore. Excuse me. Okay, we reproduce our graphs using, in this case, Salis entropy, and we see exactly the same results that we had at the beginning for the original entropy that we defined. And now we were going to explore what happens with Q is very close to 1. And in this case, we're going to have two solutions. For Q, because we have this curve, it means that we have two sets of Qs for both entropies, the one that we called S, the one that we called H, and they are going to have also information about how the game as a whole in the world has been developing or evolving. When we get these Qs, how do we calculate the entropy here? For each year, we calculate the Q, and then we calculate the entropy. It is not that close to what we saw at the beginning. So the first lesson is that we have strong correlations in chess. These correlations have evolved into, let's say, from being very strong to be less, a bit lighter. Just 1 minute for complexity indexes. The main idea of complexity indexes is that complex systems cannot function when the system is very ordered, entropy equals to 0, or it is very disordered. The entropy is the maximum, it takes its maximum value. Here it is like this in the zone where you can have, let's say, complex systems living. We're going to use two of these indexes, Shiner, Davis, and Langsberg. These are, look that we have, this is normalized, this is the entropy, 1 minus the entropy, and it will make the game of making this curve. So what we see is, look at the colors. Purple, okay, this changed a bit, but this is the first era. Then you have Potevnik era. Then you have Karpov and Kasparov era. And at the end, you have the new generation led by Carlsen. And so what we can say is that complexity is increasing with time. We have a second indicator, which is Lopez, Rees, Mancini, and it happens about the same thing. So while correlations are decreasing, complexity is increasing with time. So from here, we just have some conclusions. The first move is the most relevant of the game, first. The second, white have low diversity, high preferences. Black has high diversity, low preferences. We have large but decreasing correlations in the game as a whole, and we have an increased complexity in the let's say in the evolution of the game. So it was everything, but I want to invite you to the Enredando, the school on networks and complex systems, which is going to be in Viçosa, Brazil, this year, July. This is the address, and that's all. Thank you very much.
Right, now we have. Yes.
So in recent years, there have been very young players.
Yes.
So have you noticed some difference in the way they play or not?
Okay, yes, there is a difference, but it is a global difference. It is not just the players. And when you have young players, and it is very important what you say, you know that, okay, they should be brave in openings, but they are not as brave as Kasparov and Karpov were. So there was the time of the consolidation of openings. So let me show you, okay, let me show you just with this one. This one, okay. The early time, okay. The Russian school, there is a massive effort to improve theory, to have very strong players. This is the time of strong players in terms of a deep knowledge of openings. And we have a new time in which the opening is not that important, that relevant, but the mid game and the end game. And I just want to stress that with one more figure. This is one. Okay, you just have to remember what happened with the matrices. Just let me do it easier. Okay, let's look at Karpov's matrix. You see just 4 different first moves in all of his professional life. It is not just 1 year. It is all of his professional life. 8 different moves from when he played blacks. And then you go to Carlsen. This is really a lot of diversity. It means that the opening starts to be not that important, but the mid game and the end game start to be really important.
Thank you, Rafael.
Thanks to you. Ah,
¿Cómo se con el ganchito este? Ah, sí.
Okay, the next 2 polls will be presented in Spanish.
No, en English.
In English? No.
What is the name?
Our next speaker is Professor Carlos Chimbay.
Sí, no sé, a veces una pantalla no es
Ah, ok. Ok. Eh, I appreciate very much the invitation to give this talk. The title of this talk is Time Temperature Scaling in Complete Systems, a New Property in Nature. This work was realized in the or performed in the context of the Econophysics and Sociophysics group in researching in the Department of Physics, Universidad Nacional de Colombia. The first part of this talk is remembering about time fluctuation scaling and time tail scaling, two properties of the complete systems well known. And the second part, the main goal of this talk is to present a new property of the complete systems that we call time temperature scaling. This time temperature scaling is defined by a power-law relation between the temperature of the complete systems and the mean. The idea is to show that this property is present in different systems, in financial, economic, epidemic, seismic, other kind of systems, and establish a comparison with the time fluctuation scaling, because this property is different. I will present some aspects about time fluctuation scaling and time tail scaling. Next, I will go to, I will explain about temperature of complete systems. Then I will go to, or I will show what means time temperature scaling in different systems and some conclusions. The first part of this presentation is associated with the time fluctuation scaling and time tail scaling. What is fluctuation scaling? This idea was presented by Taylor in 1961 in this paper. It's not possible to go the proper, is possible, is
Easy solution.
I mean, I saw the.
I didn't decide it was that good.
Yeah, earlier, we would have drawn. He has a strong reputation, crossing, making corrections on expensive, yeah. That's not really
okay. Taylor in 1961 discovered this law in the context of the entomological populations. The idea is the appropriate of these populations has a random behavior. The fluctuation scaling is a idea very simple because it's a relation, a power law relation between the variance and the mean. In this paper, published in Nature in 1961, is for different populations, entomological populations, Taylor showed that it's possible to establish a power and exponential of the power law relation for different kind of population. For instance, mollusca, insecta, different systems, similar, and over here is the figure of log. This power relation is a linear, and the idea is to know what is the value of the constant and the power and the exponent. But at that time, this was established in the context of the ensemble, same systems at the same time, but in the context of the time series, non-stationary time series, the idea is that we have the same power law relation, but variance is a function of time, mean is a function of time, and the exponent is a function of time. For a same window, mobile window, we have running the time, and it's possible to determine how is the variation of the mean, the variance, and establish a fit to obtain the form as the exponential is running in the time. This property is present in different systems, for example, in ecology, in neuroscience, turbulence and percolation, website visits, reverse networks, highway traffic, financial markets, in different kind of systems, but it's possible to try to describe the origin of this property in the context of the statistical physics. In this work, entitled Temporal Fluctuation Scaling in Non-Stationary Time Series using the path integral formalism, we explain how is the variation in time of the mean, of the variance, and the power law relation, specifically of the exponent of the power law relation. We use empirical data. We establish a model founded in the path integral formalism, and it was possible to explain or to describe better the behavior of the behavior of the time in the behavior of the mean, of the variance, and the power and the exponent of the power law relation in the time in comparison with that empirical data. The model was good because the description is acceptable, but well, for instance, here is the evolution of mean in time, in particular with the UK pound sterling to US dollar exchange rate. Here is the evolution of the variance for the same. For instance, here is the evolution of the variance of the time series of the Sao Paulo Stock Exchange measured daily. The next is an example of how is the evolution of time of the exponent of the power relation. For this case, the Dow Jones Industrial Average measure. Now, respect to the tail scaling, time tail scaling, the tail index is defined in this form. First, tail the tail index is a measure of the inequality of pattern distributions, for instance, income distributions, wealth distributions, is an alternative way to measure the inequality similar to Gini index, but the tail index is defined in this form. The tail index has entropic motivation because it's defined in terms of the entropy index. Here, XTS is the k-seed value of the diffusive trajectory time series at type t. This is the mean of the diffusive trajectory time series at type t. And m, defined in this form, n minus t plus 1, is the total data number of diffusive trajectory at time t. Here we are working with that, not with the original time series we use this algorithm. This algorithm is known as the diffusion algorithm. The idea is using this form that is defined in this figure, it's possible to obtain the trajectory, the diffusive trajectory time series for different time series. And we obtained that the diffusive trajectory time series doesn't present the property of time fluctuation scaling. But for 48 diffusive trajectory time series, we prove that there exists a power-law relation in this form. This is the index tail normalized to the maximum value of the tail index in type 1 in the setting where T is 1 in the diffusive algorithm, and this is the mean as function of time, and this is the maximum value of the mean. You can see that this form, this relation has a form of the second phase transition. Beta is the exponent of the tail temporal scaling, or the time tail scaling. We call this relation as time tail scaling. And K1 is the constant of this relation. Here we are presenting, or I am presenting the different behaviors of the normalized tail index as function of the normalized mean for diffusive trajectory time series of volatility for Colombian peso dollar, Bitcoin dollar, euro dollar, pound sterling dollar. And in all cases, we can see that the behavior of the empirical dates that are very good in relation with the fit. Here is the similar for the case of the diffusive trajectory time series of volatility for silver, gold, crude and commodities, and the treasury yield of the United States taking time 100 time steps. Here is the case for the case of the low return, absolute low returns in both cases. And here we present for different time series the values of beta, the exponent of the time tail scaling, and the constant of the relation. We can see that the value of the beta is close, relative close in this range, 0.4, 0.2, more or less. Here is for the, this is for the case of volatility, and this table are the results for the absolute log returns for different cases. Financial systems, here is the Bogota temperature, Bogota precipitation, COVID cases, COVID deaths in the United States. This means that this property is present in different contexts. Now, I will go to explain, or I will go to speak about this new property that I will present now. To do is necessary to define the temperature of the complete systems. A temperature of complete systems is a concept that is not developed in the literature, and we propose this possibility to measure the temperature of complete systems. You see, this is the absolute difference between the date and the mean. And this is the probability. This is the mean. The mean will, in the next figure is mu. But it's possible that if, here, in this relation, m is the range number, and it's possible to say that if m is equal to n, then the number of agents in the system, the number of agents in the range is 1, the probability of the agent is 1 over n, the number of agents, and now the temperature of complete systems has this form. You can see that this form is the first absolute central moment. The first absolute central moment is a measure of the dispersion that which is different to the standard deviation of the variance. Have we used this concept in the context of the images, image processing, and this quantity is particularly useful for measuring the mean absolute deviation. Because this quantity can offer a more robust estimate of dispersion compared to variance or the standard deviation. In the case of distribution with heavy tails, that is the case of the time series that we will study. The analysis of the time series in financial, economic, epidemic, seismic systems leads us to find this power-law relation. Temperature of the complete systems satisfies this relation respect to the mean, the constant, and the exponent of the power-law relation. This property is called as time temperature scaling. For instance, SP 500 stock index present the typical fluctuation scaling, time fluctuation scaling, but this is the standard deviation, this is the mean, and in the log scale, this is the line the line, and this is the calculation in the time. Time is running with mobile window of 3,725 data in the case of 44,073 data in total. Running the time with mobile window is possible to find for each mobile window the value of the exponent. In this case, with the R squared with measure the quality, the feed quality. And here is the variation of the standard deviation in the time. But in contrast, now using temperature of complete systems, defined as we present, as I present as the first central absolute moment, we can see that the exponent is different of the exponent of the time fluctuation scaling. Yes, is different. And but here this is the average, the R squared mean. In this case is of 1998 one, and for the fluctuation scale is 1994. Is better in the case of the temperature. In similar way, for Nasdaq stock index, this property is present. This is the case of the time fluctuation scaling, and this is the mean of the R squared, and this is the case of the temperature, the time temperature scaling case. The mean is better for R2 squared, and the same with the DAX stock index, is the same with gross domestic product per capita. Next talk, Alejandro will speak about this case, but in the context of the scaling, fluctuation scaling, the time fluctuation scaling, but here the mean is similar of the R squared value. Here is for the case of daily COVID-19 infection cases in the world for 189 countries. The mean of the R squared is 0.82, and for the case of the time temperature scaling, the average is better of 99. The same for the case of daily COVID-19 deaths in the world. The mean of the R squared is 0.51, and in the case of the time temperature scaling, the quality of the fin is better. For instance, here is the case of magnitude of the squares in Colombia in this period. This is the case of scaling fluctuation case. This is the R square mean, and it's better in the case of the time temperature scaling. This is the case of magnitude of the squares, and this is the case of dip of the squares in Colombia. The dip of the squares for the same period. This is the R square mean for the fluctuation, for the time fluctuation scaling, and this is the R square mean for the time temperature scaling. You can see that in all cases, is most robust the time temperature scaling in respect to the time fluctuation scaling. Time temperature scaling is a new property of the complete system. Complete systems studied throughout non-stationary time series that receive this property. For the time series studied in all cases, the time temperature scaling is characterized by a power laws that present better qualities of fit with respect to those obtained in the time fluctuation scaling. In the above sense, it is possible to affirm that the time temperature scaling is a property that is most robust in complete systems studied with respect to the time fluctuation scaling, and a task to be carried is to study this property using the path integral formalism. Okay, thanks.
Thank you, Professor. May I ask you, how does the fluctuation of the economic temperature you define in non-equilibrium, not equilibrium models, could explain the transition from Gaussian distribution to power law behavior observed in financial data?
Mm, eh, Financial, this case of stock indices, the time series is non-stationary. For low returns higher to certain value, the behavior is a power law, a heavy tail. The description of this behavior of this kind of stock index in the middle for low and middle values of the low return index is possible to explain using the Levy distribution. But the tail is a power law, but in the case of the economic system, the temperature of complex systems for this financial time, the financial systems, we've called financial temperature. But in this case, in this example of economic system, the temperature of the complex system, we call this temperature as economic temperature. What is the difference? That here we are considering the gross domestic product of 180 countries, starting in 1960, and the last case is 1924. The number of data is 110, and the idea is to running the time with using a mobile window of 20 years. This value of the exponent power is the exponent of the power law relation is obtaining using only 20 data of mean and temperature. But this is the difference.
Thank you, Professor.
Thanks.
Aquí lo iba a dañar. On fire.
Next speaker is Alejandro Riescos Ochoa.
Ok. Bien, buena tarde a todos y todas. Bueno, yo voy a presentar un estudio termoestadístico y algo relacionado con el escalamiento de la fluctuación temporal del GDP per cápita de 105 países del mundo durante el periodo de 1960 al 2023. Esto es parte del trabajo de investigación que estoy haciendo con el profesor Carlos Quimbay. Bien, entonces voy a empezar por dar como un resumen del trabajo. Se divide en dos partes. La primera es relacionado al escalamiento de la fluctuación temporal. Luego mirar unos resultados en relación al Producto Interno Bruto per cápita. Y la segunda parte es el estudio termoestadístico del Producto Interno Bruto per cápita, en donde voy a dar un marco teórico del ensamble canónico para dar sustento al estudio termoestadístico del Producto Interno Bruto per cápita y concluyo. Entonces, en resumen, nosotros hicimos un estudio econofísico de los datos del Banco Mundial del Producto Interno Bruto per cápita de 105 países que registran datos desde 1960 hasta el 2023. Inicialmente se va a ver un estadístico que se va a medir, que es el promedio del Producto Interno Bruto per cápita y luego la varianza. Y posteriormente se va a hacer la relación entre la varianza y el producto y el promedio, donde se va a ver una ley de potencia entre estos dos estadísticos. Posteriormente lo que se hace es tomar una ventana de 15 años desde el 60 hasta el 74, mirando la relación que existe entre la varianza y el promedio y se va a analizar cómo cambia la constante de proporcionalidad y el exponente a lo largo del tiempo. Entonces se va a observar que existen como un fenómeno de anticorrelación entre el exponente y la constante de proporcionalidad. Y la segunda parte tiene que ver con una definición, un estudio termoestadístico del Producto Interno Bruto per cápita, definiendo la temperatura económica, la entropía de Shannon, perdón, la temperatura, la, mm, la, el- la entropía económica y el potencial químico económico para dar cuenta de que uno puede estudiar este sistema desde las variables macroscópicas em, desde una perspectiva prácticamente econofísica. Bien, entonces, lo primero es hablar rápidamente sobre el escalamiento de la fluctuación y lo que es ligado a lo que dijo el profesor Carlos, uno encuentra el escalamiento de la fluctuación o conocida como ley de Taylor, como esta relación en la que la varianza de la variable aleatoria tiene una ley de potencia con el promedio de la variable aleatoria, donde A es la constante de proporcionalidad y alfa es el exponente. Hay dos tipos de escalamiento de fluctuación. Uno es el escalamiento de la fluctuación de ensamble y otro es el escalamiento de la fluctuación temporal. Para que esta condición se dé, básicamente tiene que existir que si uno saca el promedio de la variable aleatoria por ensamble, y la define como mu, y la varianza de la variable aleatoria por ensamble, y uno lo define como sigma cuadrado, si el sigma cuadrado, es decir, si sigma cuadrado sigue una proporcionalidad con mu a la alfa, entonces uno estaría hablando del escalamiento de la fluctuación por ensamble. Y por otro lado, el escalamiento de la fluctuación temporal tiene que ver con que los promedios de la variable aleatoria en el tiempo, si uno lo define como mu y el promedio, la varianza pero temporal, lo define como sigma cuadrado y se da la relación de ley de potencia, entonces estamos hablando del escalamiento de la fluctuación temporal. Teniendo eso presente, entonces nosotros recogimos la data del Banco Mundial em, en la que se presentan registros desde 1960 al 2023 de 105 países. Acá hay un mapa de algunos de esos países. Es más fácil notar los que no están. Por ejemplo, Venezuela, Argentina, no presentan datos desde 1960 al 2023. Y, por ejemplo, la parte de Europa Oriental tampoco presenta esos datos. Entonces, con esos datos, mm, vamos a partir de ahora, para que lo entiendan, vamos a definir la variable x sub i en función de t como el Producto Interno Bruto per cápita, donde i es el país y el t es el año. Entonces, el primer estadístico que nosotros obtenemos es el promedio del Producto Interno Bruto per cápita dado por esa ecuación a lo largo del tiempo de 1960 hasta el 2020. Ahí ustedes pueden observar algunos periodos de crecimiento, de estabilización de crecimiento y otros de mayor fluctuación. Esos cuatro periodos que se observan ahí son periodos de crecimiento. Hay un periodo de crecimiento del Producto Interno Bruto per cápita desde el 60 hasta 1980. Luego hay un periodo de crecimiento desde el 80 hasta el 85. Posteriormente del 85 hasta el 95 crece. Se mantiene ahí como en un crecimiento, hay un punto, hay un periodo de estabilización hasta el 2001, luego crece muy rápidamente desde el 2001 hasta el 2008. Este es mm, este momento histórico es cuando hay un crash ahí financiero, dime.
Lehman Brothers.
Bien. 2008 y luego hay otros periodos de alta fluctuación desde el 2008 hasta el 2020 y esto es después del COVID, donde hay un crecimiento. Bien, y cuando uno mira la varianza, pues vean que es un comportamiento similar de la varianza del Producto Interno Bruto per cápita. Noten nuevamente, hay un crecimiento desde el 60 hasta el 80, del 80 al 85 hay una disminución, del 85 hasta el 95 hay un crecimiento, una estabilización y bueno, ustedes pueden observar que hay como un comportamiento similar. Ahí los tienen como para que los comparen. Y cuando entonces nosotros hacemos la relación entre la varianza del Producto Interno Bruto per cápita con el promedio del Producto Interno Bruto per cápita, encontramos una relación ley de potencia dada por la constante de proporcionalidad como 1,0256 ese es el promedio, a la 206. Esos son 64 datos desde el 60 hasta el 2023. El coeficiente de determinación da 0,9946 y el porcentaje de error está en el 6%. Esto ya nos da un indicio de que existe un escalamiento de la fluctuación temporal. Entonces, posteriormente a esto, lo que se hizo fue tomar ventanas de 15 años del 60 al 74, mirar si existe el escalamiento de la fluctuación temporal, luego se corre la ventana del 61 al 75 y uno puede observar cómo va cambiando el exponente y la constante de proporcionalidad en el tiempo. Este punto, por ejemplo, este punto azul se refiere a el exponente de la relación entre la varianza y el promedio. Para la primera ventana de 15 años desde el 60 hasta el 74. Noten que el exponente está cercano al 2,1. Luego se corre la ventana, entonces este punto sería del 61 al 75 y uno puede hacer eso con todo el registro y uno observa que pues el exponente presenta unos ciclos de crecimiento, luego un ciclo de gran aumento para el año del 94, un segundo mínimo, el primer mínimo está en el 86, el segundo mínimo en el 2002, luego un máximo relativo para el año del 2009 y luego decae para el año 2018, perdón, 2019 y vuelve a subir. El promedio más o menos se mantiene en el 2,06 y lo mismo uno puede hacer con la constante de proporcionalidad. Vean que presenta como un comportamiento anticorrelacionado, solo que el eje está logarítmico para la constante de proporcionalidad. Bueno, eso sería la primera parte. En relación a la segunda parte, entonces voy a mostrar un marco teórico relacionado a la termodinámica del ensamble canónico para determinar la energía, la entropía, la temperatura y la energía libre de Helmholtz para hacer la termoestadística del Producto Interno Bruto per cápita. Entonces, de el ensamble canónico, nosotros recordamos que la termodinámica estadística de un sistema de n partículas se describe a través de la función de distribución de Gibbs, en la distribución de probabilidad de Gibbs, que está dada por P sub j, donde j pues, es el microestado accesible del sistema de n partículas, eh, donde esa probabilidad es a la menos beta, la energía sobre la energía del estado j sobre la función de partición, que depende de las tres cantidades macroscópicas, la temperatura, el volumen y el número de partículas. Beta pues es 1 sobre kb T, J es el microestado con energía de sub J y Z la función de partición que está ahí. Bien, la energía interna del sistema de n partículas está definido como la sumatoria de la probabilidad por la energía del microestado. Y se puede obtener esa energía interna a través de la derivada de la función de partición, la menos derivada de la función de partición respecto a beta. La entropía, recordarán que se puede obtener como esta expresión, la sumatoria de la probabilidad de que el sistema esté en el estado J por el logaritmo de esa probabilidad. La temperatura, el inverso de la temperatura se puede obtener a través de la derivada parcial de S respecto a la energía, manteniendo el volumen y el número de partículas constante. Y la energía libre de Helmholtz se puede obtener a través de esta relación. Y cuando uno obtiene eso pasando la función de partición allá, entonces uno puede obtener la energía libre de Helmholtz como la energía interna del sistema menos la temperatura por la entropía. Si el sistema de partículas es independiente, es indistinguible, uno puede decir que la función de partición del sistema de n partículas se puede escribir a través de la función de partición del sistema de una partícula elevado a la n. Así, entonces, ahora, si uno llega y divide, eh, por ejemplo, la energía libre de Helmholtz en términos de n, uno puede encontrar esta relación en la que μ va a ser el potencial químico, manteniendo pues las condiciones anteriores. U sobre n sería la energía promedio por partícula. La temperatura, pues no se divide. Y acá la entropía sería la entropía por partícula, donde esta energía sería la sumatoria de la energía de la partícula por la probabilidad de que esté en el estado I, por la probabilidad de que esté en ese estado I. Y la entropía de la partícula se puede escribir en términos de esta expresión. La función de distribución de ese sistema de una partícula se escribe así y la función de partición de una, perdón, la función de partición de una partícula se escribe así y la función de distribución de probabilidad se puede escribir de esta manera. Entonces, teniendo eso presente, cuando ya vamos a aplicar esto al sistema econofísico, definiendo la temperatura económica como el primer momento absoluto, como se vio en la presentación anterior, donde él en este caso es el país, uno puede encontrar que la temperatura económica presenta este comportamiento que es muy similar al que vimos con el estadístico de los estadísticos anteriores. Vean que se encuentran las mismas épocas históricas de aumento del 60 al 80, el decaimiento acá, el aumento del 85 al 95, el aumento del 85 al 95, la estabilización entre el 95 hasta el 2001. el crecimiento después del 2001, la fluctuación entre el 2008 y el 2020 y el aumento posterior al COVID. Ahora, entropía económica, definida así, ya no está la constante de Boltzmann claramente, donde L pues va a ser el país, y M es el número de bins. Nosotros encontramos que la entropía de este sistema también, digamos, va creciendo. Y digamos que puede ir describiendo como el número de estados accesibles del sistema. Y finalmente, el potencial químico económico, que pues está definido así s- a partir de ese marco teórico del ensamble canónico. Entonces encontramos que el potencial químico es positivo desde el año 60 hasta el 75, pasa a ser negativo después del 75 y sigue siendo cada vez más negativo hasta el año 2023. Em, bueno, entonces, con estas variables macroscópicas, entonces, pues lo que uno puede llegar a concluir primero en la primera parte es que el Producto Interno Bruto per cápita exhibe un escalamiento de la fluctuación temporal donde el exponente y la constante de proporcionalidad están anticorrelacionados, tienen ciclos anticorrelacionados. Y lo segundo es que utilizando las variables macroscópicas termodinámicas, uno puede describir el sistema económico, econofísico em, sí, econofísico, démosle. Y ya, gracias.
Pregunta es, ¿cuánto es el ensamble canónico? O sea, cuando uno plantea el ensamble canónico, siempre piensa en, tengo mi sistema en equilibrio con un baño, ¿cierto? ¿Cuál sería ese baño acá?
Em, Sí, efectivamente, pues este sería como 105 países, sería como el sistema cerrado. Em, Habrían varias posibilidades, podrían ser los otros países que nos están considerando ahí. Esa es una posibilidad, sí.
Entiendo, pero su merced ha explorado si estos ciclos de anticorrelación, relacionamiento podría tener alguna ligadura respecto a los ciclos de deuda o de liquidez de la liquidez global más o menos, por
Mm,
promedio que relaciona la literatura macroeconómica, tal que pues, o sea, de esas ventanas de 15 años podríamos, o sería interesante inferir estadísticamente una cierta periodicidad para volver a ver
ujú,
cuándo puede aparecer, de modo, o sea, bajo el criterio pues en los que seleccionamos estos países y pues la influencia que tienen como ensamble. Asimismo, ¿por qué no considerar el ensamble gran canónico, teniendo en cuenta que este es un reservorio abierto para buscar equilibrio térmico y químico? Pues lo digo porque me parece curioso el comportamiento del
mm.
potencial.
Bueno, la primera pregunta, sí, no he explorado nada relacionado a mirar temas de deuda de países. No lo he hecho. Em, lo segundo es que sí, en este problema uno está considerando 105 países. Entonces recordarás que el sistema gran canónico, mm, los países o las partículas tiene la posibilidad de que entren y salgan partículas al sistema. En este caso, no. O sea, son 105 países en todo el recorrido.
Y que pena, por esa fluctuación de agentes económicos,
Ajá.
podríamos inferir un poco de la dinámica de un determinado país, por ejemplo, Argentina dentro de la TAM, que no suele reportar esos datos.
Sí, claro. Entonces, a ver, bueno, o sea, no. digamos, uno lo que podría pensar es que tú tienes los 105 países y los otros países, pues los consideras como el baño térmico. Eh, ya si tú quieres estudiar un país, pues habría que mirar ese registro de los otros datos, claro. Pero uno, o sea, lo externo uno lo considera como una totalidad externa. Mm.
No, gracias, Alejandro.
Las siguientes presentaciones están por ahí cerquita. Y no puedes ir
Es que también, o sea, lo digo porque, pues, pero entonces, no puede estar Después, pero estamos ahí, se los fallos. Sí. No, es concepción, claro, o sea, claro, porque pasa, es algo a la ocupación, pero en términos a estado de pero no lo hacen.
Sí, sí, el exacto. Pero Dios profesores pueden tener una y por ejemplo, la prueba de orden de dimensiones, en un particular caso, que así, la verdad, es una fase sólida. El mente sobre el 2 etapas, una empezamos terciaria y se llama acción exámica. Y puedes tener otro parámetro no orientacional, no orientacional, que orientacional. No, bueno, no vas a ver. Bueno, algo no, tiene que ver con la orientación del virus. Eso va a estar a larga distancia en los organismos. Y no diría, es una simetría por computación que son bien. Pero lo mismo es claro contigo, el centro de liberación. Tengan cuidado, claro, ¿cierto? Ese y creo que es de carga también.
Pero también las estadísticas que en el caso de
entre la fase de alta densidad y la de minúsculos, Felipe, ¿cómo estás?
Yo no alcancé a pensar. Sí, hay más
Pero
yo salgo de aquí a las 5:15, tal vez. Todavía estoy en la ¿Me esperas? No. Yo voy a llegar a 5:15, más o menos. Sí. Bueno, es que. Vale, de los que hablaron ayer, porque no sé qué tanto. Sí, bueno.
Y entonces dice que tiene una polaridad y a la derecha y a la izquierda.
Ahora sí.
Entonces le pedís que se vaya a la izquierda. Ya la única posibilidad que y ahí se acumula. Y bueno, igual está.
Ahora mañana. Y una cosa que no entiendo. A ver si puedo estar.
¿No tienes clase?
No tengo. ¿Qué tal todo? ¿Has estado en estos en los tutoriales? ¿Que no están?
Sí, en los lectures de... Sí, estuve.
¿Están chéveres?
Sí, estuve. Sí, de machine learning, que lo está dando de sistemas desordenados y todo equilibrio.
Todo estaba súper chévere. Me gustaba estar aquí.
Estuvo bonito. Pero hablo más que todo de problemas clásicos, entonces no sé qué tanto hay con el que interesado. Por lo que usted se habló de cosas cuánticas.
¿De qué?
Está publicándolo. Ella está en Francia, en la Sorbona, creo que. Y yo lo conozco porque ella es argentina y ella es amiga de Karen Halber. Entonces yo lo conozco por eso. Esa es la conexión, la Argentinian Connection. ¿Qué te tocó echar? Sí. A mí me tocó mañana en la última sesión.
Pues eso hicieron conmigo.
Bueno, pero no es bien.
Pero usted se queda para la cerveza, entonces.
Pero eso es hoy. O sea, bueno, es que hay un buen reception. Algo así.
¿Ah, sí? Hasta yo estaba molestando.
Sí. Pero eso, mañana
Bueno.
no hay nada, mañana es aburrido.
Lo siento. Pero seguramente tú estás más fit para estas sesiones, ¿no? Pero son como Data Integral Approach, bla.
No, son 45 minutos entre no,
Sí, no, yo no. Hasta hoy a las 6 de la mañana terminé esas. Esa mierda, o sea, qué cosa.
no, yo dije, yo voy a poner 10 diapositivas y ingeniería de computación
Sí, eso es lo más sensato.
y ya. O sea, es mejor un broad overview, explicar a la gente, porque algo así. Porque es que el contexto no da para conocer de todo. Porque nosotros no hacemos como todo está.
Cuando ella me dijo, me faltan 5 minutos, yo estaba en la introducción y yo. Hace rato no me pasaba eso. Pero bueno. Ese es el problema de dar charlas cortas después de las largas. Ay, ¿qué más?
Bien, ya nos vamos. Mañana va a ser horrible porque tengo clase de 6:30 a 8.
Tu día favorito.
Sí, y luego tengo que
Tú estás a las. Claro, es que es tarde.
Claro, no, pero
Y luego en la última.
vengo a esta, al último tutorial de Machine Learning.
Ujú.
Y luego a las 10 salgo a preparar clase porque a las 11 tengo mecánica. Entonces a 12:30. Y a 12:30 me voy a preparar la charla que es a las 3.
O sea, lo que hice yo hoy.
Y que sea lo que es que no. Creo que aquí no hay muchos de esas. Entonces puedo chamullar. Puedo
Seguramente.
precisionar.
Los vas a, exacto, confundir
Sí,
y vencerás.
exacto. Espero que esto no esté transmitiendo.
Está en verde, sí. Está en la máquina.
Ok, como
Pero estos chinos de Moderna está súper mal, mal. Hoy les puse algo como, les dije, bueno, cojan la ecuación de esta y cojan una solución por partes, de separar la parte de y separen la.
No, es que están viendo, estamos emocionalmente ecuacionando. Solo han visto con el cálculo integral que al final ven un poquito de diferencia. Listo.
Pero yo les hice ese cálculo, se lo hice en mi carrera en la clase final.
Es que no, es que no. Mira que si yo me cambio, les estoy diciendo, bueno, escribamos la diferencial de esta función de superiores. Es que estamos. Ay, me quedo. Me duele el brazo, alcanzo a estar así. Entonces, ni siquiera imagínate, yo les estoy preguntando algo que tengo que diferenciales parciales. Yo les estoy preguntando denme la diferencia, no resuelvo nada, denme la diferencia en función de X y Y. Hay un problema mecánico.
Eso es más avanzado.
Sí, se me está pasando. O al mismo tiempo que
No, es más avanzado. Yo les pregunté ya, ustedes ya vieron mecánica, ¿no? Pues,
ah, sí, porque están dando esto y aún las con.
claro, uy, no, o sea,
Es que eso estamos hablando del comité, pero hoy, o sea, uno, se confunde porque el primer curso teórico está ahí, pero no,
es 11 de proceso.
pero listo, porque no,
No, pero mira que hoy China Estados Unidos, porque yo no entiendo esto, pero no resuelto esto con este método método de residuales, yo no sé qué, ¿verdad? Y al final, bueno, yo no me acuerdo de eso, y le daba, o sea, ella sí sabía, pero sí, o sea, pero yo no me siento así, o sea, que a bajar
Sí, eso es chévere.
eso parece. Desde el máximo de
ah, bueno, yo no sé a esta parte por el examen de doctorado.
Pero más,
Por la
o sea, mantengo
de eso,
primera experiencia, pero parece que están como tratando de arreglar la cosa. Están haciendo como un acuerdo en la facultad para arreglar cómo se la paz. Yo para que no,
porque pues no,
le echan esto y le mezclamos. La verdad, y también estar, no sé, también da perspectiva. Es como estamos los problemas son,
Estás tirando el
sí, o sea, que uno ve problemas serios, pero también tiene perspectiva, o sea, no es distinto, son acciones.
No, ya no puede ver todo.
Y como bien, pues ya sabes ver,
Claro, yo voy a
no creo que deberíamos sí, están fuera. Entonces uno también puede estar un poco consciente. Exacto, esa cosa, sí, como que no se siente tan grave todo, ni tan personal.
a veces mejor para que no me
Al final,
Voy a llamar a esa la que vaya sí, sí.
Sí, no, cuál.
We are doing a 15 minutes break today.
Yeah, certainly, because now we are kind of like.
Yeah. There is a reception later.
It is, right? Yeah.
So, yeah.
So why perception? So we didn't have a time to meet, but I just came today, so.
Okay, I'm Bruno.
Yeah, Gabriel.
Gabriel.
Oh, Juan.
Juan Gabriel.
Was your part of your talk this evening?
Okay,
Good morning, very nice.
thanks.
Yeah, I tried to learn that. It's not
Okay.
complicated.
Yeah, it's a field that moves fast, so you always feel that you are catching up. You never feel that you have read everything.
Because, yeah, because ChatGPT 3, yeah, it works in the core, works completely different.
Yeah, exactly. Yeah, a lot of things have changed. Yeah. And,
It's something like a diffusion model or something.
yeah, diffusion as well.
That's hard.
Yeah, I haven't worked on that, but that's also one topic that has attracted a lot
That's
of
kind
people.
of the most recent kind of approach, right?
So I think there are people working on transformers and people working on diffusion. I think in parallel, these are the two main hot topics, I would say. Going.
Yeah, maybe tomorrow, maybe you're gonna be tomorrow.
Yeah, I'm gonna be tomorrow. Yeah.
Maybe tomorrow we have a coffee.
Sure. Yeah, sure. Yeah,
Okay,
happy to.
vamos a empezar, por favor, toma asiento. Sí. So we are ready to start the final session of the day. So we have Bruno Loeiro again. So he's going to talk about scaling laws and effect of shallow networks, neural networks. So you have half an hour, and I'll give you a 5 minutes.
Yeah, thanks. Great.
So floor is yours.
Thank you. So yeah, back to machine learning theory. So while most of the stuff that I've been telling you about in the lectures is kind of maybe 5 to 6 years old, this is very recent. So this is a work that we submitted for a conference called iClear this year. And yeah, it's going to be presented actually next week in Rio. So yeah, happy to present this today. So this work is motivated. I'm going to try to make some connections to the lectures because there are some connections, especially on the technical side. But let me first give you a motivation from the learning side. So there has been like a lot of work trying to connect spectral properties of the weights of neural networks with the generalization. So as we discussed in the lectures, we would like to understand generalization. And one way that people have been trying to understand why neural networks work so well when they train is by trying to connect properties of the spectrum of the weights to the generalization properties. So in particular, there is one line of work that's quite old and has like this group has been doing a lot of
theory on that is work by this group of Mahoney, who is in Berkeley. And they created a package that essentially you connect this package to your neural network. And then when you train the neural network, essentially saving the weights, and then it's computing like the singular values of the weight, or the eigenvalues of the weights transpose, and then just plotting. So it's like saving and plotting during the training. So in the beginning of the training, the network is random. So the weights behave pretty much like the weights of a random matrix. So just like has like some kind of bulk behavior, very much like Marchenko-Pastur-like. As you keep training, what they have observed is that in the early phase of training, there are actually different phases. And in the early phase, some eigenvalues start bleeding out of the bulk. And then at some point they detach and they separate. So this is one of the first phases of training. And they claim that these eigenvalues are correlated with the feature learning. So the fact that the network is adapting to the data. So these eigenvalues somehow carry information about this adaptativity, some information about the data. Then as you keep training, these eigenvalues keep popping out, you keep bleeding, and at some point, they coalesce back to the bulk and develop a fat tail. And the authors claim... Oh,
the bath is Marchenko-Pastur?
So in the beginning, yes.
Yeah.
Later,
no.
it kind of gets deformed. And so I don't think in these works they have any description, analytical description. Pretty much this is empirical observation. So they tried this with several networks, several architectures, several data sets, and they claim this is a bit like phenomenology in physics. They say, okay, given these observations, let's try to do a phenomenological description of what is happening. And they claim that essentially you should stop training when you start developing these heavy tails. This is the moment where you generalize better. So it's just like empirical observation. Okay, so this is the first observation that's kind of seems to be robust, and we really don't understand whether this is true or whether there is anything like on the weights, on the tail of the distribution that is actually connected to generalization. This is just an empirical observation. And they have some theoretical work, but as I said before, like phenomenological. Now, if you go to the theory land and you think about works that have connected spectral distribution of the weights to the generalization properties, there is not much out there. And this is because essentially most of the theory that we know how to do for neural networks has focused on what I was discussing in the lecture, which is you fix the weights, okay? And then you try to say something about like a network with random weights. And of course, if you assume that the weights are random, you're not going to observe this kind of phenomenology that I told you before. So this is the line of work on Gaussian universality that we were discussing this morning, essentially showing that using universality you can describe the generalization of neural networks, but this generalization lacks this adaptativity side. There are deep versions of that, but again, for random weights, there are like kind of kernel descriptions, but again, no adaptativity. And then there is the phenomenological works that assume that this phenomenology is there and try to draw some consequences. But this starts from the weight. So there is no microscopic theory in some sense of this behavior.
They looked at the eigenvectors as well, or not at all?
In this work, I think they look at the eigenvectors associated with the spikes. Mm-hmm. And the claim is that these eigenvectors have some correlation with some underlying structure of the data. Now, since this is real data in these observations, it's hard to make quantitative exactly what is being correlated with what in the data. But as we're going to see, in our case, we're going to be able to be precise about that. So the second motivation, and this is a major, let's say, observation in the machine learning, let's say, experimental machine learning over the past few years, it's about neural scaling laws. So maybe you have seen this before. If you haven't seen, I'm going to try to give you a taster of that. Essentially, in the early days of deep learning, there was a belief among practitioners that the more the better. So if you have a network and you make it bigger, it's just going to do better. Or you have some amount of data, you increase the amount of data, you're going to generalize better. Now, what these people have observed, essentially, again, empirically, is that this is not the case. If you don't scale the parameters of your network properly, you're going to hit bottlenecks. So essentially, so this is a paper by OpenAI, so they have the resources to do this kind of experiments. They take large language models like GPT, they train, they increase, for example, they fix the data set size and the number of parameters, and they start increasing the compute. And they see that the performance, so that's the generalization error, goes down up to a certain point where it plateaus and becomes constant. And then they say, okay, now let's increase the data set size. And then the plateaus goes down. And by just playing with that, they came up with a phenomenological description of these curves, which basically says that the risk, so the generalization error, is like a constant plus a power law behavior in each of these three factors. And then they fit these coefficients, like they fit these powers, and then they use this to choose how they train the next generation of models based on these coefficients so that they can allocate the resources properly. Let's say they have a certain amount of data, which is the full data of the internet. You cannot collect more data than that. So they say, okay, there's no point about increasing the number of parameters in the network beyond a certain point. Because if P and N T. Sorry, P. So P is the number of parameters, N is the number of data points, and T is the compute, the amount of compute you put in during the training. And so let's say that you fix the compute, you fix the number of data, then there is no point about going below a certain number of parameters, otherwise you're just going to hit a bottleneck and the error is not going to decrease. And this has been very, very influential because, as you can see, like training these models is very expensive. And by knowing this law, you have a way of saying how much resource you have to allocate to each of these things, depending on the constraints that you have. Let's say you have a fixed architecture, you have a fixed data set. There's no point of putting more compute than a certain amount given by this law. So again, this is empirical. And since 2021, there's a lot of interest in trying to describe this scaling behavior. Where this comes from, because it seems also to be something very robust. You try different, like transformers, you try these with convolutional neural networks, and you observe always this kind of scaling behavior. So yeah, that's a very good question, and always I feel kind of nervous to speak about that in front of physicists because you cannot see. So there is a better that you cannot see. I could see. But the powers are very small. Yes. So it's crazy because you speak about this in front of machine learning people, they just like accept it. You speak about this in front of physicists, there is always someone in the audience that is going to point, is this really a power law? Yeah, exactly. So I'm not going to get into this discussion, but I think that physicists should seriously try to do that. Unfortunately, it's very expensive to do that. Like we cannot do this in academia, right? This type of experiments. But there should be some, and by the way, we're being recorded, right? Okay, I will tell you this after. Not now, okay? But there is something to be said about this. Okay, so again, meanwhile, in the theory land, what do we know about scaling laws? Again, most of the theory has been done either for kernel methods and linear methods, which are non-adaptive. And in this context, actually, we have understood very well this type of bottlenecks for non-adaptive methods. So here is an extract of a paper that I wrote in 2021 with some collaborators. And we were able to show that essentially this kind of scaling behavior and bottleneck arises in this kind of non-adaptive methods. And in somehow, like what we want to do in this work is like to say, okay, as you train the network, can we understand how this emerges from the training? And can we understand like to connect the evolution of these exponents to properties of the weights, like in the first slide that I showed you. So that's the goal of the paper. Because here we basically only understand this type of behavior in models which don't have this adaptivity. And this is not satisfying. Okay, so by the way, there are not only transitions between different exponents and plateaus, but also transitions between different exponents. This is a whole phase diagram that depends on the noise level of the problem, the target, and so on. I'm happy to talk about that. I'm not going to go in detail because we don't have time. But I really like this line of work, so I'm happy to chat offline. So, okay, spoiler for today is that we have one model where we managed to connect the spectral properties of the neural network in this model to the power law behavior of the generalization error. And we have a full diagram with different behaviors, different scalings, and these scalings corresponds to well-defined regimes in the spectral distribution. And these regimes correspond more or less to what was observed by Mahoney in these empirical works. So that's where we're going to get. And from now on, I'm just going to motivate you. What is this model? How does it look like? And how do you get these results? So here we go. As I try to motivate in my lectures, if you want to make progress in machine learning, we need three things. We need a hypothesis class, an algorithm, and a model for the data. So let me give you these three things, what we do in this paper. So we are going to be looking at supervised learning, like in these observations are mostly supervised tasks. Data is going to be, again, X in RD, Y is a real label. And given the hypothesis, okay, this is what we saw this morning, we're going to be considering empirical risk minimization on a parametric hypothesis class. And we are interested in the risk. So this is exactly the slide that I showed in the morning. So now let me give you these three ingredients. What are the three things that we consider in our work? So for the hypothesis class, we are going to be looking at two-layer neural networks, which is, I claim, is the simplest nonlinear model to study. And as I told you before, like most of the works that have been done about that, and this is what we are studying in the lectures in the morning, consider fixed weights. So we don't want that. We want actually to be training the weights. So we want to have this feature learning. Or people have also considered training the weights, but in the linear case. But then it's just like matrix multiplication. So it's essentially linear. So it's not so interesting. So here we are going to be considering one case that I claim we can fully describe the training of both weights. And it's not a linear case. So it goes beyond the linear case. What is that? You might guess is like a quadratic network. So it's the first nonlinear thing that you can think that is beyond linear. So we are considering a very artificial network. So I don't claim that this is a good network. So already no one uses two-layer neural networks, just to be clear. And taking the square activation is even like a major simplification. Because if you just have like square activation, you can only fit degree 2 polynomials of the data, right? So it limits the expressivity of the model. Like this is a poor hypothesis class. But it is a nonlinear hypothesis class where I claim we can say we can fully describe the training of both weights. And actually you just need one weight because since this is quadratic, essentially you can absorb the other weight. So this is our architecture. And now let me give you a flavor of why we can analyze this model, this quadratic neural network. Essentially, the idea is that this is a model, this is a linear model in disguise. So if I define a matrix G, which is X transpose plus identity over square root of D, and I define a matrix S, which is W transpose W, then my hypothesis is just the trace of the product of these two matrices. So this quadratic network in disguise is a linear network, but not on the weights W, on W transpose W. So I have, in the space of S, the problem is linear. So if now I write the empirical risk minimization problem in this space, I have this problem. And notice what happened here. The regularization was the square norm on the weights. But the square norm on the weights become the nuclear norm on the product of the weights. And this is crucial because the square norm encourages having elements which are dense and small, while the nuclear norm encourages sparsity on the spectrum. So from the point of view of this matrix, this problem is enforcing sparsity on the spectrum. So this is kind of a way of seeing, what is the bias that you're going to get? You're going to get matrices which have this sparsity. And notice that this is a convex problem on S. It's not convex on W. So there is only one, if the minima exists, the minima is unique. And this single minimum S corresponds to a degenerate minima on W, right? Because there are many W transpose W that give you one S.
Yeah, what's the point of adding a linear confinement if you already have something quadratic? So that I don't understand. Why.
So in the original problem?
No, here,
Yeah.
I would have thought the lambda term would be, the strongest in case the parameters escaped somehow. But here it seems that you already have something quadratic, so it will always beat the linear term, or.
So essentially, the original problem is not. So the original problem has something quadratic, right? The original problem is this one. Let me maybe, yeah, the original problem has theta square. It's when we go to this space of S that it becomes the nuclear norm. And whether this term dominates or not depends on the lambda, right? I can always choose lambda in order to play with that. But the whole point is that if I want to control the magnitude of the weights W, this corresponds to controlling the sparsity of the spectrum on S. This is the key observation here, is that there is this sort of, in one space is sparsity, the other space is just like a quadratic confining potential. Okay, let me go back to where I was. Okay, so this problem is convex on the cone of positive semi-definite matrices. Okay, so this is the hypothesis. What is the data model? Now, this is I could take a generic data model, but the point is that since I just have a quadratic network, I can only fit quadratic functions. So without lot of generality, anything that is not quadratic is just noise from the perspective of the square laws. I can define in terms of like the inner product with respect to the Hilbert space of L2. I can decompose into the part which is quadratic plus non-quadratic, and the non-quadratic part in this norm is just like an additive noise. So, as I was discussing in the morning, when we fix a hypothesis, in some sense, there's a natural teacher model for this student in which the problem is interesting. So I'm going to assume that my data comes from a model which is itself a quadratic model on the space of W, or a linear model in the space of S. And here, the hypothesis I'm going to be imposing on this S is that this S decays as a power law. So why this is an hypothesis that I could think as making sense? So first, I want to describe this scaling behavior, so I need some sort of scaling on the target function, and why putting this makes sense. So I can think about like this target, this square target with a decaying coefficient, as a sum of different tasks that I want to solve. Each of these tasks is a quadratic task, and each task it's organized in a hierarchical way where some tasks are more important than the others. So to learn the target, I need to learn these different tasks, and some of them have higher amplitude, some of them have less important amplitude. So I can think as this power law as being essentially a sum of transitions where I'm learning, each of these individual tasks. So this is what we call an hierarchical multi-index model. So it's a special case of the multi-index model that I spoke this morning, where you have an additive structure, and this structure is hierarchical, where the first coefficient is more important than the second, is more important than the third, and so on. Okay, so given that, using these ideas from statistical physics, like large aviation theory, I claim that in the limit where I take n, d, and p to infinity with fixed ratios, I can characterize the asymptotics of the risk. And moreover, so this generalization error of the minimizer converges to something which is deterministic, and I can characterize this quantity completely as a function of low-dimensional order parameters or summary statistics. So this is just like, again, bread and butter of the statistical physics approach to machine learning. And what is very interesting here is that I can also characterize the asymptotic spectral distribution of the weights. And the bottom line is that the estimator, so the minimizer of the problem that I showed you, is essentially a thresholding function of the original matrix that I want to recover plus some additive noise in the sense of matrices. So it's the original task plus some noisy version of the matrix. So I add a GOE matrix, and then I'm thresholding on the spectrum. So this is what is called the soft thresholding function. So essentially, my predictor is seeing a noisy version of the task, and then it's thresholding at some point. And okay, this is a bit abstract. Let me show you a video. So this is a case where it's not hierarchical. I just take S star to be a Wishart. So that's just for illustration. So the target, has some zero eigenvalues and has some bulk. And then in black, I'm showing the predictor, what is being predicted. And here I'm showing the error as a function of the number of samples. So let's see if this works. Yeah. So my predictor, as you increase the quantity of data, is fitting the bulk and then thresholding and setting some values to 0. And the more data I have, the better I threshold. So I'm getting more and more zero eigenvalues. So I'm fitting both the bulk and the zero eigenvalues. This is like a simulation from the formula that I gave you. And this corresponds to having better and better error. So from this formula, essentially, I can get this plot. And let me now discuss this phase diagram and what these different regimes mean in terms of weights and in terms of power loss. So let's take some cross sections of this diagram. So let's take a cross section of this part. So here on the bottom, you see the number of samples. So larger the n, the more information I have, so the better I should be doing fitting. And here's the regularization. It's exactly the parameter that we had there. The larger the lambda, the more sparsity I impose on the spectrum of the matrix. So here I am I'm not regularizing a lot. It's almost like lambda equals to 0. So what happens here is that as I increase in the number of samples, I go from a rate where essentially I'm just fitting like the bulk. Then here, as I increase the number of data, I have some spikes that appear. Then these spikes get more and more important. And as I threshold, I'm losing some spikes, but I'm also losing the noise, right? So I'm thresholding the bulk. The bulk is the noise, right? So I want to get rid of the bulk and I want to just keep the spikes because the spikes are these directions that determine hierarchically the task. So, however, if I just threshold at a random point here, I might kill some spikes as well. And the more data I have, the better I have a separation between bulk and spikes. And so I can get rid of the bulk without losing too much. And this corresponds to a transition in the rates going from a slow rate when you have little data to a fast rate when you have a lot of data because of this separation. Now, what happens as I increase the regularization? So if I increase the regularization, I am improving like this thresholding because I'm encouraging more and more sparsity. So actually, if I fit the regularization optimally on the right place, I manage exactly to separate between the bulk and the spike. So in this region where I'm properly regularizing, I'm completely killing the bulk and I'm just keeping the spikes all the way through. And again, I get a transition between a slower rate, is lower but faster than this one, and a fast rate. So this is the well regularized regime. And the sweet spot actually is that you are here, right? You're not like regularizing a lot, but you're also not under regularizing. This is the sweet spot, is to be in this line when you transition between the two. And in this line, we have actually 3 transitions between like 3 different rates. And it's quite interesting that these things appear here. So let me give you a little bit of an intuition about this, but now in terms of the formulas. So essentially the asymptotic risk is given by these 3 pieces. So here is essentially an integral over the semicircle law, but it's an integral that goes from some value to 2, so it doesn't go from the edge to the edge. And this is where I'm thresholding. Then there is one part which is the part of the spikes which I'm not fitting, and one part which is the spikes that I'm fitting, which are given by these sums. Yeah, good. I'm almost done. Okay, so this part is the part that fits the noise. And the part that fits the noise leads to overfitting because I don't want to learn the noise part. The second part are the spikes which I'm throwing away by thresholding. So it's the part of the signal which I'm throwing away. So these are the features which are not learned because I'm throwing away. I'm throwing it with the bulk because I'm thresholding at some value. And then there is the part that I'm learned, which governs the approximation errors, the learned features. And the goal is to choose lambda such that this is as small as possible and this as well is as small as possible because I want this to be part of the green part and I still want to get rid of that. So essentially here you see that if I properly choose the regularization, which is essentially the scale, the right scale of the regularization is the square root of d, where d is the dimension, then I manage to completely get rid of this part, and then I just get the spikes. And this corresponds to the upper part of the diagram. So this is the bottom part of the diagram, this is the upper part of the diagram. And you can do simulations, and the simulations also agree well with the asymptotics. This is a bit tricky because it depends how well like things are concentrating, so you need to take a d to be large. And here, these different phases corresponds to these different phases that Michael Mahoney was observing. So you have this kind of a bleeding and then coalescence into a heavy tail. And actually this heavy tail, the power of this heavy tail is governing the power of the rates of the risk. So from these formulas, we can also ask, how does these rates compare with the optimal rate for the problem, which is the base optimal rate? So we can also compute the base optimal rate. And essentially, you can show that if you properly regularize, so if you are in this line, the rate that you achieve is essentially the base optimal rate. So this quadratic network is optimal in terms of scaling. So the constant might not be optimal, but the scaling is optimal if you properly regularize. If you don't regularize well, then you are suboptimal. Okay, so this is what I wanted to share with you today. So what did I tell you? I presented to you a solvable model for an overparameterized neural network, which is nonlinear, and which is in the feature learning regime. I explicitly connected the spectrum, so the behavior of the spectrum, to generalization. I showed you that feature learning can be understood in this problem as a cascade of BBP transitions, so these spectral transitions where the spikes corresponds to the signal and the bulk to the noise. And I gave you the scaling laws that corresponds to this behavior. So let me thank my collaborators. So Leonardo De Filippis, who is a PhD student in my group, and then Emanuele Troiani, Yushin, Jules, Vittorio, who are at EPFL, and then Lenka and Florent, who are the PIs at EPFL, and Vittorio is a postdoc, Emanuele, Yushin, and Jules are PhD students with Lenka and Florent. Thank you for your attention, and happy for the questions.
Perfect. Please. I have I'm not an expert at that. So when you show these first pictures in which you have this lump of eigenvalues that are going away to the right, you say in your conclusion it's like BBP transitions, these outliers. This I'm not, so I don't know the scalings here, but is that really microscopic, just a few of them, or is that something that is macroscopic? How many of them are there? And because I thought it was actually a macroscopic thing, and to observe such a distribution in a that would have a disconnected support, it would mean that it's a non-convex problem. So can you comment on that?
So it is non-convex on W, the problem, right? But I can comment on the so it's not one BBP transition. Actually, there is a cascade of BBP transitions, and you can compute that the thresholds for each spike getting out. And actually, there's a rate. So actually, you have something like a critical threshold. So alpha is my n over d squared because so this is the right scaling in the problem, and you have like alpha c for direction j, which goes like j to some power. If I remember well, it's like 2 gamma or something. So that's the first thing you need to prove. You need to prove that the spike j corresponding to the task direction j is going to exit at some power of j. And then you can see like as a cascade of transitions. And then what becomes tricky is that indeed, when n is large enough, it happens that this becomes like a macroscopic quantity of eigenvalues that get out, and this eventually becomes a tail. So the bulk becomes a tail. And you can cut somewhere because you're thresholding, but the number of eigenvalues that you learn are now a continuous number of eigenvalues on the scaling. And we can describe what is the rate like of the tail, the decay of the tail. So this corresponds like to the last regime that in this plot is by Mahoney. Where is it? Yeah, here.
So you do find a power law that depends on the structure of the data.
Yeah.
If the power of the data analyzed by OpenAI is so tiny, does that imply there's some kind of fine tuning, or is there some reason why the data would have a structure that
So this is a big mystery.
adds to zero?
That's a very good question. I don't know. I mean, I think that there are two big questions here related to your question. One is, where does this power law comes from? So here I introduced a model where the power law comes from a hierarchical structure of, your data has many tasks and you learn them in an order. And the power law comes from this sum of tasks. So you could see real data maybe as a sum of different tasks, but maybe the power law comes from somewhere else. Like data can be hierarchical in many different ways, and it's not clear what kind of structure in the data actually leads to this power law of OpenAI. So that's the first thing.
So if OpenAI is a log, could you make your data, I don't know, exponential distributed or something?
Maybe. I mean, I think it's easy to cook a model where you get like something like a log. But the question is first is how does it emerge? And the second, why the exponent is so small? Because in these kernel models, you get large exponents because functions need to be square integrable. But this is really non-square integrable functions with these powers, if they are really right? Because there's also the question whether these coefficients are right, whether they are doing the right fitting, right? But yeah, so these are good questions, but unfortunately, I don't have answers outside my model. Sure.
Any more questions? No? Then we move to the next speaker. We thank again, Bruno. Having the same question. Where is coming from that overall? And there is no, in the OpenAI data, there is no, there is only one decade or something in the direction. So it doesn't see, but yeah.
Yeah, we can discuss them. I have to discuss over coffee. Right?
Solo que estoy dando el
Because so these guys that will dispute this company was I
¿dónde me empieza a celular?
porque si no
Por aquí. Conéctate a mi celular. Yo tengo, pero veamos aquí. Llega un correo. ¿Sí? Bueno, entonces sí, Raúl. Yo tengo la mía acá. Sí. Porque solo para descargar la charla. Pues para hacer todo el stream. Es para hacer el stream. ¿Tienes? ¿Pero tienes esto? ¿Dónde está el? Espera, ¿puedes conectar la internet de este? ¿Y le conectamos? ¿Tú necesitas? Este es el que. Entonces necesitamos otro cable para conectarlo. No, Sí, no va a pasar el chat, sí. Ah, pero lo puedo pasar, pero está en Keynote. No, no, entonces sí toca muy. Entonces, registrar. Yo antes tenía semiconductor. Hace mucho tiempo. Ah, pero bueno, me lo puedes pasar a mí. Ah, pero yo ¿tienes descargador de eso? Sí, ese descargador de USB-C. Sí, si quieres me lo pasas a mí. Ah, si quieres me lo pasas a mí, yo tengo aquí. Ah, bueno, listo. Vamos. Y yo te puedo conectar a la. Yo no sé, pero esto sí se va a descargar eventualmente. A ver. Intereses. ¿En serio? Bueno, dale. Pues, eventos académicos. Bueno, ¿qué más? Entonces, inicios de sesión. Tiene conexiones. ¿Qué haces? Ahora, ¿dónde? Ah, ya. Señalación post. No te bolso, pero sí tu bordo. Creo que ya está. Bueno, necesita micrófono. Okay, so we have our next speaker. So Juan David Munoz. So he's going to talk about the cross relationship applied onto harmonic oscillators on the Brownian motion. So 15 minutes. I'm going to give you a minute here. 30 yours.
Okay, so thank you very much for the opportunity. So, un moment. Yes, okay. Okay, this is the undergraduate thesis work of a student of mine, Juan David Jimenez, who nowadays is making his PhD in Cornell. And it's a very simple application, no? So the thing for fluctuation theorems, and this is only to see that we can do it with the computer, that's all. So, to explain what the cross relationship is, I will use a pedagogical view introduced by Ian Ford from the University College in London. And it's very simple. What we have to use is an harmonic oscillator, a mass plus a spring on a thermal bath, and that's all. So what is the idea? The idea is that in the overdamped limit, you only have the position. No? So the position is the only canonical variable. And the spring constant is the only thing you can change, yeah, to make work. So let's say that you have some protocol and you start with the spring with some initial distribution for the position, and then you maintain the spring constant for a while, and then you change it to another one and change to another one, and we want to compute the probabilities to go from here to there, to there, to there, and to cross all these paths. So what will be the probability to have that path? Will be just the probability of starting here times the probability of moving from here to there, and so on the end. So you can change, you can think now into perform the protocol in the reverse way. So in the reverse protocol, you start by keeping the spring constant in Kn, yeah, and take Kn minus 1 and so on, and to reproduce the protocol backwards, in the reverse. And then you can compute the probability to perform the same path, but in the reverse way. And then you have that probability. Okay, so you can define that a single path. Again, so just by summarizing, I will summarize all these transition probabilities. Just for the notation, I will push all of them in a single element that we will call W4 from x0 to xn, yeah? So it's just multiplying all these transition probabilities, and the same for the reverse path. So now let's define what a reversible path is. So a path is reversible if that probabilities are equal. If not, you can define what is the total entropy increment that is produced when you perform the forward protocol. And this is defined as K Boltzmann times the logarithm of the probability for the forward path divided by the probability of the reverse path. And that's all. If you accept that, yeah, I can derive a lot of things. So the trick is good. Okay, so let's start by saying that in the case of a spring in a thermal bath, these transition probabilities are well known. This is an Ornstein-Uhlenbeck process, and this is the solution. So the solution is that the mean, this is a Gaussian, and the mean value of the Gaussian, yeah, decrease exponentially to 0, no? So the point where the spring doesn't do any force, and the width of the distribution goes exponentially to a limit value, and the limit value is the one that in equilibrium has an harmonic oscillator, and that's all. So if you use that solution and you put it over here, no, you will obtain that if you take two of these transition probabilities, so the forward and the backward transition probabilities, and you compute that, you will obtain that this is just the difference in the energy, in the total energy, minus the difference in the energy that is produced by changing the spring constant only. So this is the work, and this is the total energy. And the difference will be the heat. So what you have here is that, summarizing, K Boltzmann times the logarithm of the transition probability on the forward protocol divided by the transition probability on the reverse protocol is just the heat divided by the temperature. So what you have here is the entropy increment on the thermal bath. And then if you reproduce that, if that is the increment of the energy, the entropy increase on the thermal bath, that is just the entropy increase on the system. So this is the reason why this is the total entropy increment. Okay, we can say something more, because this is that, and this is that. No, if you have a Boltzmann distribution, then the total entropy increment is just that. That is the increment in the work produced performed on the system minus the difference of free energies between the initial and final ensembles divided by temperature. Okay, so we can use that result to derive the Crookes relationship. So we have that, yeah, and let's compute the probability to perform some work. Everything is at constant temperature, no? First, okay, I mean, it can be out of equilibrium, but at constant temperature. So the thermal bath is at constant temperature. So let us compute the probability to perform some amount of work on the forward protocol. So it will be just to add the probabilities to perform each path and only to maintain alive that ones who has exactly that amount of work. That's all. So you can multiply and divide by the probability to perform the reverse protocol, and then you can identify that, no, as the exponential of the entropy increment, and then you can put it here. And because of the delta, you can take that away, and what you have is that one. So it's very simple. Then, of course, sorry, because of the Spanish, of course, the work in the forward protocol is minus the work on the reverse protocol. So you can compute if you identify that, yes, because of the deltas, you can reverse that. You can identify that that is the probability to perform a work minus W on the reverse protocol. What you obtain is this one. So that the probability to perform some work on the forward protocol equals the probability to perform minus that work on the reverse protocol times that exponential. That is the Crookes relationship. Yeah. And the Crookes relationship, yeah, was experimentally tested for the first time in 2005 by the Bustamante group, yeah? And it was on an experiment like that, like this. You have a bed, two beds. One of that is fixed to a piezoelectric to measure for the force. And the second one is trapped by an optical twister. And then you pull the twister and see how much force do you need. and then for a RNA molecule to enlarge and to separate a little bit, no? And then you come back, and it's supposed that the RNA molecule closes again, no? What will be the differences? Okay, and so you can see by looking at the work, yeah? This is the force against the position, and you will see some jump, no? This jump is just because some kind of bond is broken. And then when you come, this bond comes back. No, this is not the links here, no? Is more on the way they are pulled, how do you say? Sipping, yes, exactly. Sipping and unsipping. Yeah, okay. So when you have this curves from force against position, what you have here down is the work. So you can compute the work done forwards and the work you did backwards. And then you can repeat that many times, and what you have are histograms. So if you do it very slow, no, you will have just a delta. Or let's say the histograms for forward and backward protocols will be the same. Better. But if you do it faster and faster, what you have is that, for instance, for the green or red histograms, you will have that they divide. No, they are not the same because you are running very fast, you are out of equilibrium. And then, according to that, when these two probabilities are the same, this will be zero, and it means that the work you are measuring equals the free energy difference between the initial and final distributions. So by looking on that, no, for these points, you can measure the free energy difference. But if you want to do it better, you can just divide this you can take that, divide for this, and take the logarithm, and what you have is a straight line. And the slope of that line will give you a better measurement of the free energy difference. So in the last 20 years, this is a usual protocol in biophysics. Everybody uses that, and it's very good. I mean, you can measuring free energy differences just by changing a single nucleotide here. Yeah, for instance, an in for one in. And then you can change the energy difference, and the simulations fits very well with molecular dynamic simulations. Okay, so what we did. So this is, let's say, a toy model for studying how that works on a simulation. So what we have here is two springs. Let me show you it better here. What we have is, okay, sorry. Well, we have these two springs joined by for another one. So just to know that everything runs fine, the first thing is which thermostat are we using? So what we use is this leapfrog thermostat that reproduces this Langevin equation with an external force. And what we have is that this damping constant produces an alpha, and this alpha you use it here. And this epsilon is normal distributed, no? With mu equals 0 and sigma equals 1. And then with this protocol, you can simulate, for instance, free diffusion only. So what you have for the position is what you expect, no? And what you have so it's free diffusion is a Wigner process. And what you have for the velocity is an Ornstein-Uhlenbeck process. So everything is running fine. So now we can use it. So how is the model? The system is composed of two harmonic oscillators joined by a spring.
So the idea is the following. For a single harmonic oscillator, the free energy is that, no? For two harmonic oscillators, two coupled harmonic oscillators, what you have is two normal modes. So this one and the other one, that's faster one. So the free energy differences will be this here plus something, and this something is important because the energy you have here and there, yes, when you have zero velocities is different. So in equilibrium, the energy here is different than that. So you have to add for that energy differences also to compute the free energy. So, and now the protocol. The protocol is as follows. Let's start with the two harmonic oscillators. This is the here and there. So, and they are coupled by this spring in the middle. And then we will start to pull them apart at constant speed. No, you can do it very fast or very slow. And in certain moments, when the distance between these two masses equals the length, the rest length of this spring, the spring disappears. So the spring breaks, and then you have these two harmonic oscillators moving apart. Then you wait a little bit, and then you come back. And then for the reverse protocol, you take the two free ends of the springs and take it, and you start to put them together again. And in the moment when this distance among the masses, between the masses, is the same as the resting length for that spring, the spring reappears. And that's all. So, and now let's go for the results. So this is what happens when you go very slow, and this is what happens when you go very fast. And then you can compute, for instance, the work when you go very, very slow will be equal to the free energy difference. And this goes perfect. I mean, the theoretical value is that one, and the experimental value from equilibrium is this one. Just for looking at that everything runs fine. And then now finally we can go very fast. So out of equilibrium. So if we go out of equilibrium, the average path for the work will be this one, and the backward will be that one. And then if you compute out of equilibrium, what you obtain is what we expecting. In equilibrium, the two histograms are more or less the same. And when you increase the speed, so you will have the red one, or the green ones, or the yellow ones, and they all cut themselves more or less around the same value. And if you measure, you compute the log, or the logarithm of the forward probability divided by the reverse probability against the work, you obtain the straight line you needed. And by looking on the slope, you can compute the free energy difference, and this is 1% inside the 1% error from the theoretical value. So everything runs fine. Yeah. So it's a very simple example. It's a toy example just to show how everything works, and that the intuition works properly, and that you can use these simulations to compute free energy differences. So what we want to do is to use that from granular media. In that case, the distributions the temperature distributions are completely different because these are the force ensemble and the volume ensemble, and we will see what we do with that. So thank you very much.
We have time for just one quick question.
Yeah.
Then I will ask just one short question. Your definition of the work at the finals or almost final slide was not exactly the one that you advertised in the beginning. It looks like the heat.
Huh? Which one?
Oh, yeah. Just this one up there. This is force times displacement. And you said, oh, this is not the right work. The work is actually variation of the stiffness times the energy.
Okay, here no, this is the force times the position. Yes. Yes, and the work is the area below. Yes, sorry.
Okay, let's take a point again.
Yes, you're right. This is the cumulative work.
Where's the next speaker?
That's the work. It works in so what is dragging box? In this protocol, it works as literally dragging the screen. Yeah, it's actually.
Yes, the final, you are right. The final is it's not force, it's the work, the cumulative work.
No, but it's
Huh?
Who's Julian looking for?
I don't know.
Okay.
He's starting now. He's in the first year.
Yeah. I did my PhD.
Okay. So perhaps I can may I put him in contact with you?
I'd be happy to answer any questions.
Okay.
My advisor is just retired. You finally retired in January. He was supposed to have retired for like 3 or 4 years.
Bueno.
¿Pero vas a hacerlo desde aquí?
No, pues esto es esta. Cargámoslo de una vez. Ya la puse aquí. Esa está muy chévere.
Ábrelo con o bueno, en fin.
O le podemos dar este avance, ¿Dónde lo paso?
Okay, so we go to the last talk for today. It's going to be now we are
Yo también lo pongo en la.
Y es algo raro.
Sí. Ok.
It's from David and Gomez. Feedback control and the second law of thermodynamics in a ratchet physical system. So floor is yours, 15 minutes.
Sure.
I give you 5 minutes.
Okay. Hello, thank you for being here. Today I will show you what I did in my undergraduate thesis, and it's very close in spirit to the work of Jose Daniel, that was my advisor. So, I would like to begin with an experiment. Suppose that you have a colloidal particle, and that particle is subjected to random forces because of the collisions with the water molecules. Additionally, suppose that that particle is heavy, so the weight is appreciable, and that we confine that particle with an optical tweezer. Optical tweezers are widely used in biophysical experiments and mesoscopic physics experiments, and they are very nice because we can model them with an harmonic potential. That particle, under such external forces, can be well described with the overdamped Langevin equation. Here we have the restoring force of the optical tweezer. There is the weight and the random force. Okay. As Jose Daniel explained, I used the same algorithm, and this is like a benchmark of that the algorithm is working properly. This is the case of free diffusion. Here we have thousands of trajectories. There we have the evolution of the probability distribution into a Gaussian from the delta distribution. And here we have the variance with respect to the time, which is linear. And also we have the Ornstein-Uhlenbeck process, where the mean velocity goes to 0 exponentially, and the standard deviation goes to a constant value, also exponentially. Now, I want to control that particle in a very clever way, and that is with some feedback control or protocol. Suppose that you have your thermodynamic system, and your variable of interest is the vertical position of the particle, which I will call x. And you measure it with some noisy measurement. That noise will be characterized by some Gaussian noise of amplitude sigma m. And that outcome I will call y. Based on that outcome, I can modify some external parameter that I will call lambda, which in this case will be the position of the optical tweezer, of the trap. And whenever the outcome of the position happens to be above the center of the trap, I will switch up the potential so that I want to satisfy a very specific rule, that the updating process has to do no work. What does it mean? That is equivalent to say that the potential energy of the particle doesn't change. And why does it not change? Because it just depends on the distance. If you see, this distance is the same as this. So when I flip the potential upwards, now the particle will be confined in a region that is above the past center of the potential. If we repeatedly do this, we can lift the particle effectively just by catching thermal fluctuations. And it appears that we are extracting energy from a single heat bath. But we will see that there is no such thing as a free lunch because that extraction has a limit, and it has to do with the information that I obtained from the measurements. Okay? This is the case of perfect measurements, but I have noisy measurements. So it could be the case that even though I measured the particle in some place, in reality, there is somehow, for example, below a little. And that updating rule wouldn't satisfy the zero work condition. I would fix to satisfy that condition for all cases, so that I have to modify how much I lift the trap. And that is controlled by this parameter alpha that I call the gain. And I will call the optimal gain the one alpha which satisfies that condition. Okay? So for noisy measurements, this alpha will be 2. Notice that for perfect measurements, the distance between this and this subsequent positions of the trap is twice the distance from the center of the trap to the particle, 1, 2. And you can understand this like flipping up symmetrically with respect to the position of the particle. But if I have noisy measurements, I have to lift up the potential a little bit less. Here is a realization of the experiment for the case of perfect measurements. And here is a realization for the case of noisy measurements. I will measure noise not with the amplitude of the Gaussian noise, but with its inverse that I call SNR, or signal to noise ratio. Okay? It appears basically the same. But the condition I am trying to satisfy is that on average, the work done in the procedure of updating the position of the potential is 0. Here I have a plot for that optimal gain as a function of a wide range of noises. Notice that for high values of signal to noise ratio, that is nearly perfect measurements, that gain approaches 2. That was the symmetric updating. And for low values, it goes down up until a critical value, signal to noise ratio of 0.63. Below that value, the only way of satisfying the condition that no work is done in the feedback process is just by doing nothing. Or equivalently, if, well, I guess that was clear. Below that value, even if I leave the trap just a little, there will be work done. And that is what I do not want. So below that critical value, I simply cannot leave the particle. And we can think of a phase transition between a working regime, which is this, where I can lift the particle, and a non-working regime below this value, where I simply cannot. Also, I can measure this is the output power average, that is just the free energy on average per unit time that I extract in this process. And we see the same behavior. It approaches some constant value, and when the noise is high, or when the inverse of the noise is very low, notice that these points are 0 because I am not lifting the particle at all. That is just fluctuating around the initial position of the optical tweezer. And now I will talk about a little bit about the second law. In the context of stochastic thermodynamics and stochastic processes, one can state the second law via using the fluctuation theorems. So first we have these integral fluctuation theorems that an equivalent statement is that on average the entropy production of any process is greater than 0. But we have to include the effect of the feedback that I am doing in my system. And we can derive, I will not go into the details of this, but we can generalize that expression to this one, where the mutual information appears. And if we define the entropy like this, and state that the work is 0, this is 0, one can derive this, somehow a generalized version of the Jarzynski inequality with feedback control and no input work. And this states an upper bound on the amount of free energy that I can gain through this procedure. The free energy in the form of gravitational potential energy. Okay? So I want to calculate that mutual information for a wide range of noises and see if that is in all cases satisfied. Here is somehow a sketch of the derivation. That is the definition of the mutual information between paths, between trajectories, where x is the trajectory for the actual positions and y is the trajectory for the measurements. This is the definition. The subscript C means control, and this conditional probability can be equal to the product of the conditional probabilities for each time step. If we do this math, we have finally this expression. I want to center on this last. This is just the Shannon entropy for an entire trajectory of outcomes. And it happens to be just the sum of the Shannon entropy of the individual measurements. What is the problem here? That the system is at all times out of equilibrium. And we do not know the probability distribution for these outcomes. So we have to estimate an entropy with an unknown probability. And that happens to be a problem. Notice that for high values of the signal to noise ratio, these terms diverge. And that is a problem, but let's remember the interpretation of the mutual information. If we have very precise measurements, both paths, the actual positions and the measurements, are nearly the same. So the mutual information between two variables or between a variable and itself is just the Shannon information. So just this last term survives. And okay. And this is the result. In yellow is just the same graph as here. And in blue is that information power, that is just the information divided by the total time of the protocol. And the inequality is satisfied by a margin, large, very large margin. And that's all, I guess. The main, in fact, that experiment was realized by John Bischofer and his group, and is very well described in this paper. And the generalizations of the fluctuation theorems with feedback and the derivation of that mutual information is very well described in this thesis by Takahiro Sagawa. And that is all. Thank you.
Thank you. We have time for questions. Yeah, the thesis director. Yes, you should ask.
Okay, of course, that the system is an implementation of a Maxwell demon because it's like extracting energy from a single heat bath, or it's harnessing just thermal fluctuations to get something useful.
More questions? Oh, the experimental setup that you explained at the beginning. Can you explain it again? I didn't quite.
This.
No, before. I think that from the beginning you showed something about the. Yeah, I think
that's just an schematic comparison of the size of a colloidal particle and the molecules. In fact, this image is taken from a course that Frederick taught here last year.
Okay. Times, we have more time for a question. If not, so we thank the speaker again. So we have reached the end of the session. So thank you, everyone. And I guess you have to.
So, on Tuesday, we have the poster session, and we have a prize for the two best posters. So we are going to announce them now. So I thank some of our speakers that were the jury, and they take a look at all the poster and talk. I had talked to the students. So suspense. So I'm going to start with the second position is the poster by Fabián Quevedo, Unraveling Dependent Statistical Features in Open Quantum System via Quantum Trajectories. So congratulations. And the surprise, so these books, I hope, would be helpful. And the first position is William Montaño, Critical Time-Dependent Phenomena in Diffusion Generative Models. William is here? No? Well, we will send him the prize. It's also a book and
a subscription to Scientific American for 1 year. And this is the second.
If some of you know it, or I know if he doesn't come for the prices. Okay, so now we have a wine reception outside. So if you want to discuss a little with your colleagues, it's there in the corridor, and You're welcome. And we meet tomorrow at 8:30 here.
Vale, gracias.
Gracias. Bueno, abrimos la sesión de Zoom.